YouTube. This is my second video in my module on finding the rate of change of graphs at given points, okay? In our last video we discussed how we could use tangent lines to a graph in order to approximate the slope of that graph. In this video we're going to discuss how we could use a secant line and the limit process in order to find or at least approximate the slope of the tangent line almost perfectly, exactly perfectly actually. So we're going to go ahead and start with this. As a matter of fact, we're going to define what we mean by a secant line, okay? So let us understand that we possibly have a curve. We could just say this is just some curve. We'll call it f, some functional relationship. And maybe I want to find the slope of the graph at this point right here. And okay, previously we had said we could find this, or at least approximate it, by finding the slope of the line tangent to the graph at this point. Now, of course, we could find the slope of the graph at this point, but we would have to find the rise over the run of this tangent line. And in order to approximate this tangent line, what we'll do is we'll actually generate what we call a secant line. So a secant line, if a tangent line is a line that intersects my graph at just this one point and has the same slope of my graph at that one point, then we say a secant line is a line that runs through it at two separate points. And so we could say this would be my secant line right here. And actually we could find the slope of this secant line, which is what we're after, or at least define it thusly, okay? And so the deal here is this secant line, I've already got a picture up here, a diagram on the left, but we're going to say this. Let us say we want to find or approximate the slope of our graph here at this point. We'll call it x f of x, okay? And also this, we have a secant line running through not just x f of x, but the point of tangency here. But we also have a secant line running through this point over here, and we're going to refer to this point as being some h units past the x value of this one. So we started at an x value of x here, and what we've done is we've gone h units in this direction. So we would say this x value right here would be the x value x plus h, okay? And we would say, well, the y value of this point up here, if the x value is x plus this distance h, we say the y value is what I would get when I plug that x value into the function. So we say it's at the height f of x plus h. But what we'd like to do is, first of all, let's define the slope of the secant line. And this is really easy to do. We'd say it'd be the rise over the run. So in order to find this rise over run, the cool thing is we already know the run is h. So here's what we're going to write first and foremost. We say the slope of this secant line right here, it's not the tangent line, but the secant line, is change in y over change in x, where we say the change in x is this unit h that we walked to the right of our original point of tangency. And then we say the change in heights, what we'd have to do is we'd have to take the height of the second point, which we said was the y value we get when we plug in x plus h. So we say f of x plus h, so this would be like our y2, minus the height of the first point, which was f of x, so minus f of x, which is y1. So essentially we could say that this is y2 minus y1, and also the run, which was the change in x, was just this distance h. But we could say that this difference quotient right here, this is what it's called a difference quotient, okay, a difference quotient. What this does is it represents the slope of the secant line, So the secant line, again, running through this point that we care to find the slope of the graph at, this point of tangency, and some other point to the right of it, h units, okay? So its slope is always this. The thing here is this. We want to use this secant line to help us approximate the slope of the graph at the tangent line, okay? So what we're going to do is this. We're going to observe the fact that the closer and closer these 2 points get with respect to h, that is, as h gets smaller and smaller, you can see my diagrams here. As h is getting smaller and smaller, you can observe what's happening to the secant line. The secant line started with the slope of, say, this right here. And as h gets smaller and smaller, you notice that this point kind of moves down, and my secant line has gotten a little bit closer to the slope of our graph. Oops. To the slope of our graph. Let me pull out my pencil too. At this point. So you'll notice that the secant line is a little bit closer to the slope of our graph here. As h gets even smaller, we notice that this point moves even closer. Now my secant line looks like this, and my tangent line looks like this. So as h starts getting smaller and smaller and smaller and smaller, you'll notice that the secant line is getting closer and closer and closer to the tangent line. Instead, what we could do is we could say, well, what if h was 0? What if these 2 points were 0 away from each other? Finally, we would have perfectly the tangent line. The only problem with this is if you were to plug in an h value of 0 over here in this difference quotient here, you'll notice that we have f of x plus h, so we'd have f of x plus 0 minus f of x. and this would be all over. We're plugging in 0 for h. If the distance between them was 0, then we'd have perfectly the tangent line, but the problem we run into here then is this. We get f of x minus f of x all over 0, which is 0 over 0. So this definition of the slope of the secant line doesn't exist at that 0 h value. So just to show you a little bit more dynamically, I did throw together a graph here, and what you're seeing is just some parabola that I put together, and what I cared to do is this. I want to find the slope of my graph at this point A. And so already what I want you to notice is I've got two things in here. First one is this. We've got this red line, and the red line is actually perfectly the tangent line. So we could say, well, to find the slope of that, we could say it's up, maybe 2 over 2. It goes to this point here. So the slope of my graph at this point A is really up 2 over 2. It's 1. Okay. But what I want to observe is this. I've also thrown in this green line here, and this green line represents the secant line, which is, you'll notice that I put the rise and run on it. Essentially what we're saying is this. As the distance between A and B with respect to H, as H is getting smaller and smaller, that is, as these points move closer and closer together, you notice what's happening to the slope of the green line, the secant line. The slope of the secant line is approaching the slope of the tangent line until H gets so small that you wouldn't be able to tell the difference between it and 0. This green line would be almost perfectly the red line until finally, click, they meet up and they become the same thing. Okay, so I'll have you notice here really quickly we say A undefined. This line up here we say A undefined. The reason why is because H going to 0 like that, we can't even find the slope of that. We can't do that. But we could say, at least we could say, what's it getting closer to, the slope of this green line, as this H value goes to 0. And in order to answer this question, we use limits all of the time to do this. So essentially, the whole crux of finding the slope of a tangent line is to use a secant line first, which we say, here's the slope of the secant line. And if we were to take the slope of the secant line and do the limit of it as h approaches 0. So as this thing down here gets really small and this thing right here gets really small, we already observed that the slope of the secant line approaches the tangent line. We say then the slope of the secant line, the limit of it as h goes to 0, it approaches perfectly the slope of the tangent line, which produces the instantaneous rate of change of our function at that point. So the definition of the slope of a graph at any given x value is this. We say the slope m, this would be this thing right here, the slope of the tangent line, which is the same as the slope of my graph, of f, at the point x, f of x, is equal to the slope of its tangent line, and the tangent line is given as this. The tangent line m, like we've said here, is perfectly just the slope of the secant line as h goes to 0. And the slope of the secant line we gave as being this difference quotient right here. So we'll just say this. We will evaluate the slope of the secant line here as h goes to 0. Provided that the limit exists, then we say this would represent the slope of my graph at that point. So this would be the overall slope. So in our next video, we're actually going to find the limit of, say, a function at a given x value using this secant line limit formula, and we'll call this the slope of a graph here. Okay, cheers.